Do they have a...
Hi, Sarah.
Very large.
What?
Very large everything.
And friend.
Dogs too. And big dogs. Big hearts.
Oh yeah, Sarah has a friend who's not in the picture.
Hey, who's your friend, Sarah?
Yeah. Oh, yeah, we've seen her before.
Person
Hello.
from
Hi, other person.
history class.
Before.
History class.
Good old history class person.
We have another student.
Hey!
That's a lot of stickers on that laptop.
Yeah.
What do we have? What is
Coexist,
the?
that's good.
What
Hey,
the,
Gambino!
Yeah, Gambino.
Yes, and on future.
What is
Way
the
to
one?
go.
What's the like cat thing on the top right?
Cat.
It says cream, which is thing, and then it says cats rule everything around me.
Nice.
Oh, an acronym.
Oh yeah. Oh,
Have you seen
it
it?
is an acronym. I missed that.
What's the acronym? Anchor.
Good morning, Anchor. Good morning, Walter.
Oh, green.
Good morning.
I felt like the bear.
How was everybody's Thanksgiving? Everybody have a good Thanksgiving?
Good until.
Yes.
Anchor, you traveled somewhere, if I remember right. Is that right?
I want somewhere far away.
No, my cousins came here.
Because.
And he cooked the turkey.
Oh, did you cook the turkey?
I did cook the turkey.
That's right. How did it turn out?
It was good.
Better than last year?
Too many. I would say it's about equal.
Oh, okay.
Okay. That'll work. Yeah, Mitchell, get the door, would you?
Yeah, I was about to.
Thank you.
Was it moist enough?
That's hard.
Yeah, it was moist. It was very moist.
You don't have a moist bird. Nothing like
Yeah.
a moist bird.
Oh, right.
My mother got a new meat thermometer, which she
Yes!
looked at the wrong end of it, and so she thought she overcooked the turkey this year.
The wrong
But it was
end.
still good.
Like Fahrenheit Celsius?
No, like. Of course I went to Allentown. Yeah,
Alright,
have the big,
back question.
have the big
Stupid.
annual
Don't football game. Cough at me.
annual football game Thanksgiving morning, 8 o'clock.
Oh, yeah,
Where's
yeah.
Dan?
No.
I think I was asleep at that point. I sort of woke up at 11 that day.
How about Dr. Fisk? How did your Thanksgiving football game
Yeah,
go?
How
did
was-
you
win?
Yeah, I'm glad you asked.
I was winning.
We won easily, 6-1. Crushed it. I threw all 6 touchdowns.
How'd they get?
Wow.
How'd they
Dr.
get
Fitz.
one
Clapping,
point?
clapping my face.
Ben Roethlisberger.
I gotta teach you guys something.
I know. So
Do you still play football with
Half of a
Vandy kids before Vandy games?
Not before it's on Fridays. We play every Friday. But we play less than we used to. It's hard to get enough people.
Dr. Fisk, can I have like an independent study with you on manners?
You could use it.
Oh.
Wow! Oh my god!
Shoot, you
We'll work
could.
it out. Okay.
I'm good with that.
I want to spend some time today. Some people said they had some questions about how the cryptography stuff is working. So I want to lecture a little bit, and then we'll kind of weave in the exercises that we have about cryptography. So we have a certain exercise which is kind of pure number theory, and then all the exercises are kind of number theory. So we'll come to that in a moment. But let me go to the board and discuss what's going on. So here's the idea. This is the idea that we saw in the reading that we were going to do, that we did for today. Okay. There's some message that you want to send to me. Okay, here's a picture of you. And then you need to send your message via the internet. Okay? So this might be an email, for example. Yeah, or Snapchat. Don't attempt to send me Snapchat.
Do you have a Snapchat?
No.
Dang.
So don't attempt to send me a Snapchat.
I'll send it to head math
It would be a
coach.
waste of time. Head math coach, that's all my stuff. Okay.
Just not coding.
So what happens, okay? What we don't want to happen, for example, is we don't want a bad guy located here
Bad guy.
to intercept this communication. right? That's the thing that we want to avoid.
Not a rat dot.
So what we want to happen is we want to create our email here, and we want to encode it somehow. We want to encode it somehow that what gets sent over the airwaves is this encoded message, and if the bad guy intercepts the encoded message, he cannot decode it. What we want to happen is we want the encoded message, I'll write this, email is encrypted. And then the encoded message gets sent over the airwaves, okay? The encoded message is received by the receiver, that's me in this case. And then I decrypt. I decrypt the message and then I decrypt. So this is the idea. We want to send an encoded message in such a way that if the bad guy receives it, he cannot decode it. So how do we do that? This is what we have in the RSA cryptography. So the idea is this. You type some message, okay? And then what you do, what happens, this is what happens. Your message gets chopped up into small pieces, into small blocks of text. And then to each block of text is assigned a number, okay? And so there are many ways that you can do this which are very simple. Okay, so for example, something that you might have done when you were very little is like, I'm going to replace all the letters with numbers. I'm going to take A will be 0, 1, B will be 0, 2, etc. K will be 1, 1, Z will be 26, 26. You definitely need that second digit there. Otherwise, if you have things next to one another, the computer, like if you have 1, 2 meaning A, B, then the computer cannot distinguish it from L, which is also 1, 2. So you definitely need this placeholder 0. This is so I don't know how many of you have the same interests that I have, but one of my interests is 8-bit video games, okay, or 16-bit video games also. But if you have an 8 or 16-bit video game, there are some emulators that allow you to pull up the hex code and edit it. So like, if there's a certain video game, like one of my favorites is the original Legend of Zelda. How many people played Legend of Zelda? Wow. That's like, boys unanimous, girls unanimously no. Walter also has not. Great game. But like, let's say you have this point in the Legend of Zelda where the old man gives you this cryptic message, right?
Yeah.
If you know what the message is, you can search the hex code for the message, which will be encrypted exactly like this. And then you can take his message and just change the letters. And then you can save the ROM and play the game, and now the old man says what you told him to say. Which is really fun to do. I really like it. Okay, so, anyway, sidebar. So you encrypt your email or whatever as some block of text. And then we need to encrypt the text. Okay, obviously if this is my code and I send that over the airwaves and bad guy intercepts, he can decrypt this message. It's not a sophisticated code. So we need to sophisticate this code. How do we do it? Okay. So that's what we're going to look at today. And this is what the worksheet described, but I'm going to work through an example with you in a little more detail. So who remembers, what was the first step? What are the things that we need to choose in order to run this process of encryption? Anybody remember? Barbara. Two really big prime numbers. Yeah, that's the secret to the whole thing. Because again, remember we talked about there's two problems that we talked about that computers are really bad at. One is factoring, and the other is computing kth roots mod n. Computer cannot do that apart from guessing check. So our first step is we're going to choose primes, P and Q, and let n equal P times Q. So this number n, who remembers what was the term we associate to this n? Anybody remember the term? Okay, this is called the enciphering modulus. Modulus in exactly the same sense of modular arithmetic. Okay, it works exactly the same way. Okay. Now, for the sake of this example, let me just emphasize that if I give a computer n, the computer cannot determine p and q in a reasonable amount of time, because the computer cannot factor a large integer in a reasonable amount. For the sake of this example, we're not going to want to use numbers that are too big because we're not going to be able to do any of the computations. But I'm going to choose, for our example, we're going to choose p is 5 and q is 11. So these numbers are not so big, but that's what we're going to want to do. So therefore, n is 55. That's going to be our enciphering modulus. And then there is another number that we need to choose, which is called the enciphering exponent. Anybody remember how we choose that? It only needs to satisfy one condition. I remember it.
Is that it has to be relatively prime to the product of p minus 1 and q minus 1.
Very good. Yes. Greatest common divisor of k and p minus 1 times q minus 1 should be 1. So as Sarah said, that they should be relatively prime. I don't know if I've used that term, but that's a good term to know. Relatively prime just means exactly this. Two numbers are relatively prime if and only if their greatest common divisor is 1. Okay, very good. And so here, p minus 1 times q minus 1 is 40. P minus 1 is 4, q minus 1 is 10. So p minus 1 times q minus 1 is 40. So I just need to choose some number k so that the greatest common divisor of k and 40 is 1. So there are many numbers that you can pick. For the sake of this example, I'm going to pick 7. I think. No, sorry. I did an example before class, and so I want to try to stick with it so I can catch myself on making mistakes. I'm going to choose 29. Okay? In particular, if k is prime, the condition is certainly satisfied. As long as it's not here. Well, as long as it's not. Well, yeah, I shouldn't have said that. That's not true. It could be that the prime number is a divisor of q minus 1. So I'm going to choose 29. In general, so like this is something a computer would have to come up with. The computer would have to come up with k. And so if these numbers are very big, it's not immediately obvious how to do that. Okay. But we can do that by the Euclidean algorithm. Okay? The Euclidean algorithm will allow me to determine if the greatest common I can pick a number and then check if it works by running the Euclidean algorithm, which takes not that much time, and then checking if the greatest common divisor is 1. So that step is computationally not that hard. It's a guess and check sort. It can be a guess and check sort. Okay. And then now what we're going to do is we're going to take a message and we're going to encrypt it and then we're going to decrypt it. Okay, so let's say this, and I'll go back to the diagram, which unfortunately I think I'm going to have to erase it. Okay. Well, maybe we'll see. Okay, so I have this email, and I'm going to say that M, let me make that a little bigger. Okay. M is the message that I want to send. Okay, so we talk about this idea, we take our text, we break it into small pieces, and then each piece of text gets assigned a number. Okay. And then we take that number and we encrypt it in some way, which I'm going to describe in a moment. And then that changes the message into some encoded message, which I will call C for code. So the message gets encoded here at my home computer, and then it gets sent. So I hope that this is, maybe I'll move you guys so it's less sensitive. It gets encoded before you send it. You have the message, I encode it, and then it gets sent. Encoded message travels. The encoded message is received by the receiver. Decryption occurs, and then you pick up the message. The receiver receives the message and can read it. So we have to understand the two-part process. We need to encrypt the message in such a way that it's hard to decrypt, but possible. That's our plan. How do we execute the plan? Well, this is so beautiful. It's so beautiful how simple it is, and yet how unbreakable it is for computers today. I'm going to erase it. I think we understand. So let's say that the message that I want to send has the number 19 associated with it. Now, I need to encode it. And so what I do to encode it is just very simply the following. And the encoded message I'm going to call the ciphertext. That's the standard term for that. To compute the ciphertext, I just take the message and I raise it to the enciphering exponent, which is k. And then I reduce it mod n. So this is what we need to compute. Now you might say that looks gross. 19 to the 29th is a huge number. How could I possibly compute that? What we'll see is we can compute this together, and we will do it, and we won't even use a calculator. We can compute what this is together with no calculator. Okay. Here's how we're going to do it. Let's look at the powers of 19 mod 55 that have exponents that are powers of 2. So here's how we're going to do it. 19 to the first, well, that's clearly just 19. So I'm going to stop writing mod 55, but all this is going to be done mod 55. 19 squared is 19 times 19. What's that? Who knows that? Don't worry about the mod 55. 361.
It's 12.
This close, Walter. This close.
It's 12.
19 squared is 361. And then now we
Say not
reduce
mod 55.
Oh. Yeah, well, reduced mod 55 is 12 then.
I don't think so.
Ooh.
What is?
Yeah, it is.
Let's think about. Okay, so we're working mod 55. That means that this is the thing that we're going to keep in our mind all the time. 110 is a multiple of 55. So therefore, 330 is a multiple of 55. So close. So 361 mod 55.
Oh, shoot, I was thinking about 19. Oops, my bad. My bad.
Oh,
Yeah. Yeah, sure.
361 is 31. Does that make sense? 330 is a multiple of 55. So 361 mod 55 is 31.
The 31th letter of the alphabet.
Everybody with me so far? Now, if I want to do 19 to the 4th, here's where the modular arithmetic really helps. 19 to the 4th is 19 squared squared. So if I want to compute this, I can just compute 31, because 31 is 19 squared. I can do 31 squared. Now, what is 31 squared? Harvard, very good. 961. We know that 990 is going to be a multiple of 55 because every multiple of 110 is a multiple of 55. So 961 is 29 less, but 29 less would be the same as 26 more because 29 plus 26 is 55. Or you could just subtract 55 from 990. That would give you 935, and then 961 is 26. So this is 26. And then we're just going to keep going until we get to exponents that are bigger than 29. We don't need to do any of those. Okay. So we'll go maybe a little more quickly. 19 to the 8th is 19 to the 4th squared. Okay. So therefore, this is congruent to 26 squared. What's 26 squared? 676. Very good, Barbara. That's awesome. Okay, 676. And 660 is again a multiple of 55. So 676 is going to be 16. Good. Good mental arithmetic day. Said Andres calculator.
Eyes in the back of his head.
And then we have 19 to the 16th, which is going to be 19 to the 8th squared. That's 16 squared.
42.
Oh, I know this one. 200.
It's
I got this one. It's 256.
What's 256 mod 55?
36.
36, good. 220.
Still minus 34.
All right, it was a good team effort.
Thank you.
Now, question. How can I use these results to compute this? 19 to the 29.
Add
No, you don't want to add them. How can I write 19 to the 29th in terms of these?
do those 16 times.
Third one, yeah, good, Ashley. Which one?
16, 8, 4, 1.
16, 8, 4, 1.
Yeah.
Right?
Yeah.
This is 24. This would be 19 to the 24, 19 to the 28, 19 to the 29. Good. So 19 to the 29 is going to be congruent to 19 to the 1st times 19 to the 4th times 19 to the 8th times 19 to the 16th. Yeah, and then we need to do this. Let's see. I think I might have picked a different M. No, this is what I picked. So I feel like this was supposed to simplify it. Oh. 29, 66. Oh. Well, okay, so let me do. Let's do it. So multiplying something by 19 is not that hard because you multiply it by 20 and then you subtract it. So let's do 19 times 36. We'll take care of the biggest one. That's 720 minus 36. That's 684.
Yes.
What is that mod 55? 24. Good, Sam. So that took care of the 19 and 36. We got 24, 26, 16. Now, here's another place I can give you a little mental arithmetic trick. How could I quickly multiply together 24, 26?
25 and 25.
Do 20. Okay.
Say again?
4 times 26 minus
20. No, it is something minus 1, but it's not 24 times 26.
1. Oh, 25.
It's 25 squared minus 1.
Yeah, right. Why is that? That's 25 squared minus 1. That's 25 minus 1 times 25 plus 1, which is 24 times 26.
Oh.
What? Factor trick. Yeah. 25 squared is 625. Minus 1, 624. What's 624 mod 55?
6 to
30, 660.
No.
So you're going to be 26 away.
No, it's
Mod
30.
right?
It's 19.
19.
Come on.
Because it's 36.
There's
backwards
36
and
away,
then
yeah.
The other direction.
So we took care of this, and then 19. So we got a 19 back. That's interesting.
Why?
20 minus 60.
It's 320 minus 16, 304. What is that? Mod 55.
30, 26, so 27. No, 29.
29. Good. So this is our encoded message. This is our encoded message.
29.
That's what we're trying
It's the same as exponent, that's a coincidence. Okay, that in general.
I'm telling you. You shouldn't make your whole.
That's my message to you.
That's your encoded message. And then, so like for a computer to figure this out, the computer would need to find the 29th root of 29 mod 55. Okay, that's very hard. That's very hard.
Can you not teach a computer to do what we just did?
No.
A computer can certainly do what we just did, and must do what we just did. The issue is that a computer cannot undo what we just did,
Oh.
right? The issue is we want, the computer wants to decode this message, but there's no way to like undo this process. As you might imagine, right? Like there's a lot of information that's being lost when we reduce mod 55. And so to get that information back would be hard. How do you get it back? Great question. That's where we're going.
We have to.
Now, we have to get the message back, so we need to decrypt it. And then this is something, so we need one more thing, okay, which the paper also discussed, which is we need what we call, I think it's called the recovery exponent. We call it the recovery exponent. How did we find that? Anybody remember?
You put the turkey in the baser.
Alright, so, okay, here's what we do. We know that these two numbers are relatively prime. So we find, so I'm going to call J the recovery exponent. Find J such that Kj plus P minus 1, P minus 1, X equals. So this is just a Diophantine equation that we can solve by the Euclidean algorithm. We can solve this by the Euclidean algorithm.
Can computers not use the Euclidean algorithm?
They do. They do.
Why are they not able to do it?
Great question. See, because so when you send the message out, here's the beauty of the whole thing. When you send the message out, an intercepting computer can know the ciphertext, okay, the encoded message that it intercepts. It can know the value of n, and it can also know the value of k. And even if it knows all three of these things, it cannot decrypt the message. It cannot decrypt the message because it cannot find J. And the reason that it cannot find J is because it does not know what P minus 1 and Q minus 1 are. Because it does not know what P and Q are because it can't factor.
Oh.
So that's the issue. That's the whole thing.
How does
Your computer picked P and Q. So your computer knows P and Q.
no? But, right.
Like if you
I
send an
it
email
you.
to somebody. Yeah.
Oh, so it's part of the program. It's part of the client software for program. So like Gmail has some program in it that generates this stuff, and it's synced up. Okay. It syncs up between the sender and there was this great discussion. I have to. Okay, so I'll think about it for next time. I'll think about it for Friday. You can in fact send it as part of the message, and the receiver cannot intercept it. I have to remember how that works. Yeah, I'll remind myself.
So it just comes down to factoring.
It just comes down to factory computers are bad factory is such a big deal. Such a big deal. And that's why, like we talked about last time, if computers ever learn, like if quantum computing ever becomes functional, then encryption totally needs to be redone. Totally needs to be redone. Okay.
It's all over.
So now what we need to do is we need to solve this by the Euclidean algorithm. And I think probably not too bad. We need to solve, in this case, 29j plus 40x equals 1. And we need to choose the value of j. And my guess would be that we can probably figure this out without actually doing the Euclidean algorithm. Does anybody, I don't immediately see a solution, but can anybody look at this and determine a solution by looking at it? I'm going to need like a multiple of 9. What's 9 times 29? 261. That's not going to work. What's 11 times 29?
And J equals 29 works, doesn't it?
Yeah, it looks like negative 11 and then 8. Is
Coincidence.
that right? Negative 319 and 320. Okay, that works. So J equals negative 11 will work. Let's make it positive. So we also talked about this idea that if I have a solution to this Diophantine equation, I can construct another by adding 40 to this and subtracting 29 from the other. So if negative 11 comma 8 is a solution, then so is 29. We're getting a lot of 29s. 29 comma, and then I subtract 29. 29 comma negative 19 is also okay. So that's what we're going to choose for J. J is 29. J equals 29 gives us a solution. Okay. Now this is something that the interceptor must never have. If the interceptor can get this, then the interceptor can decode the message. Yeah, I wish that. Yeah, I worked this example out before class, and then it didn't work out like this. Oh, because I chose a different value. I did have K equals 7, and I wanted to change it. So I mixed them. Okay, but this is going to work. So now, let's watch. All right, so actually, I'm going to audible. Okay, I'm going to audible. So bear with me. Okay, so we're going to switch back to K equals 7. I don't like that we have all these 29s. I feel like it's going to obscure. We're going to switch. K is 7. Okay. So then the solution, what will be a solution to this? If x is negative 4 and j is 23. 7 times 23 is 161. 40 times negative 4 is negative 60. So j is 20. Coming back here, now I need to compute 19 to be 7.
Every day.
Nineteen to the 7th is 19 to the 4th times 19 squared times 19. 31 times 19 is 620 minus 31. That's 589. 589 mod 55 is what? 30. And now here's a good opportunity for me to show you something else that we didn't get to see in the earlier computation. Okay. We talked about in earlier classes the idea that it may be helpful to use negative numbers in modular arithmetic. So since 39 is pretty big, mod 55, I'm going to change it to negative 16. 26 times 16 is 260 plus 156, so that's 416. This is negative 416. Negative 440 is a multiple of 55, and this is 24 greater, so I would get 24. So this is now my encoded message, 24. My recovery exponent is 23. My original message is 19. So I like that better. Now we have different values here. Sam and Mitchell, lesson. So now we have this encoded message. We want to decrypt it. Here's how we're going to do it. And again, it's beautiful how simple this is. It's beautiful how simple the idea is. Okay? We're going to take, we're the receiver. Okay, we received this 24. And then all I do is I take 24 and I raise it to the power of j. Okay? So I'm going to take 24, I'm going to raise it to the 23rd, and I'm going to reduce mod 55. So again, we're going to have this computation. Right? 24 to the first is 24. 24 squared is 576. 576 mod 55 is 26. 24 to the 4th is 26 squared, 676. Mod 55 is 16. 16 squared is 256. 256 mod 55 is 36. Then we need 24 to the 16th. 24 to the 16th is 24 to the 8th squared. 36 squared, I can do that, but let's do negative 19 squared. That's positive 361. Positive 361 is 31. Okay. So this product, 24 to the 23rd is 24 to the 16th times 24 to the 4th times 24 squared times 24. 16 plus 4 is 20, plus 2 is 22, plus 1 is 23. All right. Now we reduce, so 26 times 24, we did that earlier. That is 624. 624 is negative 36, which is positive 19. 31 times 16 is 310 plus 186, which is 496. Oh, interesting. What's 496 mod 55? 1. Yeah, good. 440 is multiple of 55, so is 495. 496 is 1 more, so we got 1. So it is 19. Which, that was our original message.
Oh, wow.
So it decrypted it, right? Raising it to that power, decrypted it. So this is the whole process. This is the whole process. You start with some message. You choose an encryption exponent that satisfies this condition. Okay? And then to encrypt your message, you simply take the message that you have and you raise it to that power and you reduce mod n. Okay? You've chosen n according to, based on your choice of the prime numbers, the large prime numbers. Which, by the way, so like, when you read these articles online that say scientists found a 12 trillion digit prime number, and you're like, sweet, who cares? Why would I ever want a 12 trillion digit prime number? That's super important, actually, right? Big prime numbers are very useful in encryption for this reason. They're harder for computers to find as factors. So I encrypt my message this way. I send my message out. Okay. And then to decrypt it, I just take the encrypted message and I raise it to the power that I got by solving the Euclidean algorithm. That's how a computer would compute the recovery exponent. It would use the Euclidean algorithm to solve for J. And then that gives you the recovery exponent. So all that I need to choose is P and Q and K. That's all that I need to choose. Once I do that, everything is determined. I don't really choose J. J is something I calculate. J.
So if you're sending the message, how do you tell like the receiving computer what P and Q are? Is that like the syncing thing that you're talking about? Really?
Yeah, I need to remind myself of that. It's like it's in sync, and actually you can include that as part of the message that you send in some way that the interceptor cannot decode it. I need to remember how that worked. But off the top of my head, I'm not. But I'll remember it for next time. Yeah, that's certainly an important question. It's like, how do you get these things to sync up in a way that like the interceptor cannot also sync up? Can be done. And there's like I think it's like there's some back and forth exchange in like sending an email. There's like several sends back and forth that happen. I'll remind myself how it works. But anyway, yeah, we see that it works. Okay, we see that it works. But then, of course, we should ask the question, why did it work? Right? What happened? And this was the purpose of the exercises. So the exercises go through in detail, why did this work? And then that's what we want to talk about today. So we have this one lemma that's part of it, and then 2 other exercises. So let me pull those up on the screen. We'll take a look at exactly what we're doing. So was that helpful? Did that make sense to everybody what we did? Okay, good. That's good. Now let's take a look.
Yeah.
Oh, sorry. Yeah, I'll throw it away. I didn't realize I
Okay, so here we see the handout. And we have this lemma. This exercise 1 is a lemma, so oh, this is annoying. Just enlarges the boundary, not the PDF. Okay, hopefully we can see it okay. Exercise 1 is this lemma, and then exercise 2 is this result, okay? C to the j is equal to m times m to the x times p minus 1 times q minus 1. So in other words, we're starting to show why the process is working. C is our encoded message, and what we said is to decode it, we just raise it to the power j. Now we want to see why that helps. So let's skip this lemma for a moment. We'll come back to it when we recognize that we need it. Who would like to show what they did for exercise 2? Anybody want to give their solution to that one? Sarah, was your hand up?
Yeah, if no one wants to, I'm not.
But see, I feel like we're in the same situation. I don't know if I got this email from you again.
Okay. Or I can just talk. It's not.
Okay,
Like-
that's true. That's true. That's true. Let's look. Okay, so here again we see the results. So tell us about it.
So we can see from the equation, the Diophantine equation, like they gave above, which is in the first paragraph of the navigation, that the x multiplied by p minus 1 multiplied by q minus 1 is equal to 1 minus kg. And then we just put that into m to the power of 1 minus kg. And then because m multiplied by m to the power 1 minus kg is equal to m to the kg, it's and because c is defined as m to the power of k, so that's true.
Good. Yeah, I think actually I should have said something a little more in the exercise. Yeah, the way that I wrote the exercise, actually, now I recognize I should have said something a little different. But let me just restate what Sarah said before, unfortunately. Sarah and I have these difficulties with email exchanges. What Sarah said is really good. Okay, we have a few things that we're kind of keeping track of, and we're starting to see the way in which they come together. We have this encoded message, C, and we want to see what happens if I raise it to the power j. Well, what is C? By definition, we compute C by taking the message M and raising it to the power k. Okay. So by definition, C to the j, I guess I should use C to the j is M to the k. C is M to the k. And so laws of exponents, this is M to the k j. And then I have an expression for kj here, okay, that comes from the Euclidean algorithm. Okay, so this is what Sarah said. This is m to the power of 1 minus p minus 1 times q minus 1 x. Okay. And then using another law of exponents, here I have I'm going to think of this as a product, and so therefore I can write it as m to the 1 times m to the negative p minus 1 q minus 1 x. Yeah, and I didn't put a negative in the handout. But really, as I wrote it, there should be a negative there. But we're going to see that the negative doesn't really make a difference. We're going to see that that's not going to play a big role. And then m to the first is just 1. Or m to the first is just m, so I will not write that. Okay. And so that is the exercise. That's exercise 2. Any questions there? All right, let's thank Sarah for chipping in. Appreciate that, Sarah. Very good. Okay, and then we have exercise 3. Okay, so exercise 3 says it asks you to take this expression and reduce it mod p and also mod q. Okay, so does anybody want to present what they got for that exercise, or how they solved that exercise? Let's just think about it together, okay? Because so now we're going to use a very important result, which we stated earlier, which is Fermat's little theorem. What did Fermat's little theorem say?
If P is prime and A does not equal 0,
Good.
but it's in the set of integers, I guess that's a given.
Yeah.
But
Well, integers mod p.
yeah, and then P, then it's equal to A to the P minus 1, and that equals 1 mod P.
Good. A to the power of p minus 1 is 1 mod p whenever p is prime and a is not 0. It's easy. So now watch what happens here. If I take this expression and if I want to reduce it mod p, it's actually pretty simple with the help of Fermat's little theorem. Okay? Fermat's little theorem allows me to say, well, laws of exponents allow me to say the following, that the expression that I have here, I could write that as m times m to the p minus 1 to the negative q minus 1 x. Right? This exponent is product, so I can think of it as a power to a power. I would multiply these exponents. But m to the p minus 1 is 1 mod p by Fermat's little theorem. So this whole expression here is just going to be 1. It's going to be 1 to this power, which is just 1. And then I still have this m in the front, so I get this m. Mod p. So c to the j is congruent to m mod p. And similarly, c to the j is congruent to m mod q, also by Fermat's little theorem. M to the q minus 1 is 1 mod q. So this term again will be 1. So now is where we need the lemma, okay? Because now we have shown that c to the j is m mod p, c to the j is m mod q, and we want to say that this implies that c to the j is m mod p times q, which is n. So in other words, c to the j is m mod n. And then if that's true, so I'm going to put a little question mark here. If that's true, then we have proved that the decryption process does what we want to do. Does this imply that c to the j is congruent to m mod n, which is p? That's the big question. If we can show that, then we got it. And that's what the lemma does. The lemma says the following, so I'll write it. It's exactly the same. If x is congruent to a mod p, and x is congruent to a mod q, then this implies that x is congruent to a mod p. Okay, and p and q are primes. That's a hypothesis. Now, did anybody prove this lemma in the homework? Lena, so would you be willing to go through your proof with us?
Yeah, I sent it to you.
Great. Yes, I did get it.
I think it works.
Okay. Yeah, there were some hints there. If you kind of follow the hints, it's not that bad. I don't know if you did or did not follow.
I did follow.
Lena Friedman. Okay, go for it.
All right, so we have the initial statement, and then we have, this was in the hints, x equals kp plus a, where kp equals 0 mod p. Or for the mod q expression, you can write x equals lq plus a, where lq equals 0 mod q, because a is the remainder when x is divided by q or p. It's just kind of another way of writing out what we mean when we say a mod q.
Very good.
But it's helpful because it means that you can say, because x and a are the same values, you can say that kp equals lq.
Good.
And since we're working with all integer values, which means that because p and q are prime, you can see when you divide the left-hand side by q, because L is an integer, that means K must be divisible by Q because P is not.
Good.
Then once you follow that, it means you can write K as an expression of Q instead.
Yeah, so let's just slow down for a second. You're doing awesome. Q must be a divisor of K, so therefore I can write this. Q is a divisor of K, so Q times some number M is K.
Mm-hmm.
Okay, carry on.
And then just by using substitution, then you can write it instead as x equals m qp plus a. And now we see again, this is another expression for x is congruent to a mod pq.
That's right. If I divide x by pq, which we see here, I'm having trouble highlighting it only, okay, but here it is. If I divide x by pq, the result is a. X is kp plus a, but k is mq, so therefore x is mqp plus a. And then if I divide it by pq, I get a. So that gives us the lecture. And that gives us the result, and that proves that the encryption-decryption scheme works as planned. Okay. Any questions there? Lena, great job. Let's thank Lena. Okay. Here's what we're going to do for next time. No homework for next time, but I just ask you to kind of keep these ideas in your mind. What we're going to do next time is we're going to break into 3 groups. The groups will be, we're going to have a sender, we're going to have a receiver, and we're going to have a hacker group. Okay. And then we're going to attempt to have the sender send a message to the receiver. The hacker will intercept certain parts of the message, and we're going to see if they can decrypt it before the receiver does. So that's our plan. That's our plan for Friday. All right. Any questions? All right. Thanks, guys. See you all on Friday. No homework for Friday. See you then.
Yeah.
I have to.
The hacker's up.
Yeah, let's check my
The hacker seconds.